Very well. The course takes a turn here. Calc 2 takes a turn. We move away from techniques of integration. We move toward these things called differential equations. Differential equations are equations where we know the derivative and we work our way backward to figure out what the function or possible functions are. And so there are two ideas relating to that we will look at early together. One is the idea of a slope field. This is a visual approach to differential equations. So for all of my friends who are visual people who need to see what functions look like, this is for you. There will be another lesson following shortly on this called about a thing called Euler's method. Euler's method is a numerical method for all of our friends who like arithmetic. So I would like to show you how to draw a slope field. Slope fields come on graph paper. So we like graph paper, have a supply. On this graph paper, maybe this is 1 and this is 2. Like it's okay to have these dots. Most of the time when we make a slope field, there are dots. There are places at which we're going to put the slopes. The question in play here, construct a slope field for dy dx is negative 2x. A slope field. So what does that mean? That means at each of the dots, we ask ourselves, what is the slope of the tangent line based on this derivative? And then we draw a teeny tiny piece of tangent line with that slope. So, for example, everywhere x is 0, the derivative is 0 because x is 0. So everywhere x is 0, we draw a little tiny piece of tangent line whose slope is 0. All of those are tiny pieces of tangent line whose slope is 0. Everywhere that x is 1, the slope of the tangent line is negative 2. And so we figure, well, this is a slope of negative 2, so it kind of looks like that. This is a slope of negative 2, so it kind of looks like that. This is a slope of negative 2, so it kind of looks like that, kind of looks like that. Everywhere the x value is negative 1, the slope is positive 2, so we play the same game over here with slopes of positive 2. That's about a slope of positive 2. That's about a slope of positive 2. And so then we just finish it up over here and over here. Slopes at negative 2 are positive 4. That's really big, really big, really big, really big. And this is negative really big, negative really big, negative really big, negative really big. This is what we call a slope field. Now, it makes sense to talk about a slope field. Take a look at what the slopes do. They start big, then they're less big, then they're 0, then they're big negative, and they're really big negative. Why? Because what are the y's that solve this? The y's that solve this are parabolas that open down. So if we were to imagine the solution curve that goes through this point, we imagine that it does something like that. We imagine that the solution curve that goes through here does something like that. The slopes are really big positive, then they're less big, then they're 0, then they're big negative, then they're really big negative. And that's what the curves look like. So we want to see in the slope field that the curves follow that pattern. If I may demonstrate one more time. Construct a slope field for dy dx equals 1 minus y. And we'll do the same dots as before. There's nothing special about the dots. It's just the area on the coordinate grid you're interested in. There's nothing special about these dots. These aren't the dots we use all the time necessarily. They're just a subset of the plane. So this is the derivative. So where y is 0, all of these places where the y is 0, the derivative is 1. So everywhere y is 0, we draw lines with a slope of 1. And everywhere y is 1, we draw lines with a slope of 0. And everywhere y is 2, we draw lines with a slope of -1. And everywhere y is -1, we draw lines with a slope of 2, slope of 2, slope of 2, slope of 2, slope of 2. It is a slope field. It helps us to imagine what the solution curves look like. So if we were to imagine the solution curve that goes through this point, we would have to imagine that it probably does something like this. We would have to imagine that the solution curve that goes through this point probably does something like this. They follow the slopes. They follow the slopes. So a thing that you can do on your own is you can generate a slope field for dy dx is x minus y. Now, x minus y is a tricky deal because, oh, whoa, I'm so sorry. Because in this example, in this thing that you do on your own, you can't just generalize and say, oh, for this x value it's this, or for this y value it's that. You've got to look at each point individually and say, all right, this is the point 0, 0, so the slope is 0 minus 0. And this is the point -1, 2, and so the slope here is -3. And this is the point 2, 1, and so the slope here is 1. And you go to every point individually and you ask yourself, what's the slope of the tangent line at that point? So that'll be a nice OYO for you to do just to practice. I would like to consider this question before we're done. This is a multiple choice question. Could be a quiz question. There's a slope field, and you're supposed to figure out which of these is the differential equation that generates this slope field. And these things are usually relatively difficult to play with, but what I have found helpful is to play four corners with it. To think about what happens at 4, 7. This is the point 4, 7. At the point 4, 7, at the point 4, 7, this is 1 minus 4. This is 4 minus 7. This is -4/7. This is 1 plus 49. And this is 1 minus 7. Well, this line has a negative slope, and it's a pretty big negative slope. That's not a pretty big negative slope. That's not a pretty big negative slope. So then we take a look at what's going on at -4, 7. -4, 7. So at -4, 7, this is 1 minus -4. This is -4 minus 7. This is 1 minus 7. That line's got a negative slope, so it's not that. So then we come play down maybe here, maybe at -4, -7. At -4, -7, this is 3. and this is 8. Well, that's not helpful. So what's going on down here at 4, -7? Well, at 4, -7, this is 4 minus -7, that's 11, and this is 1 minus, that's still 8, so that's not helpful. Well, so now I wonder, does the x play a role? Does the fact that there's an x here play a role? If I look across a y line from left to right, the x doesn't play a role. So x doesn't play a role, that's our differential equation. And so we can reason through which differential equations produce which slope fields if we're careful. Okay. Next up is Euler's method. That's part of this lesson also.